My title of my lecture is Quadrature Processes in Electromagnetic Field Problems and Telecommunications. At first, I will introduce you to some quadrature process. First, numerical integration begins by Newton's idea from 1676 for finding the weight coefficients A in the so-called endpoint quadrature formula for given usually equidistantly endpoints, tau 1, tau n, such that the quadrature formula has algebraic degree of precision at most n minus 1. It means that the integral and quadrature formula is equal for all algebraic polynomials of degree at most n minus 1. In modern terminology, given n distinct points and corresponding values of function in some points tau k, Newton constructs the unique polynomial of degree at most n minus 1, which at the points assume the same value as f, expressing this interpolation polynomial in terms of divided differences. Omega, capital omega of t, is the node polynomial, and the quotest number weights are given by formula ak. A big progress in numerical integration begins after Gauss' discovery of his famous method in 1814, which dramatically improves the Newton-Cotes method. Here, degree of exactness of the Gauss formula is 2n minus 1, which is much greater than n minus 1. An elegant alternative derivation of Gaussian formulas was provided by Jacobi, and after we have several contributions by Meller, Radau, Heine, etc. Significant generalization to arbitrary weight functions or measures was given by Christoffel in 1877. He also gave connections with orthogonal polynomials and continuous fractions. Today, this formula with maximal degree of precision, 2n minus 1, are known as the Gauss-Christoffel quadrature formula. Orthogonal polynomials as a basic tool play an important role in this field. There is a deep connection between orthogonal polynomials and Gaussian quadratures. Let w of t be a non-negative function on AB inside of R, for which all the moments mu k exist and are finite, and the first zero moment is positive. The function w is known as weight function. The inner product PQ we introduce in the usual way, and such inner product give unique system of monic orthogonal polynomials pk, such that it is a linear recurrence relation which connects three polynomials, pk minus 1, pk, and pk plus 1. It is a fundamental relation for orthogonal polynomials. Coefficients are recurrence coefficient alpha k and beta k depend only on the weight function w. A big progress in construction of quadrature formula of Gaussian type was given by Golub-Welch algorithm in 1969 in a paper in Mathematics of Computation, that quadrature nodes tau k are eigenvalues of the Jacobi matrix. It is a three-diagonal symmetric matrix with alpha coefficients of the main diagonal and square root of beta coefficients on the sub-diagonals. The first components of the corresponding normalized eigenvectors give the Christoffel numbers, the coefficients in Gauss-Christoffel quadrature formula, and we can see that this quantity is positive. It means that the Gauss-Christoffel quadrature formulas are always convergent in the class of continuous function. But this method, this algorithm enables us to construct quadrature formula, but how to construct the coefficients, it is the main problem. Because only for certain narrow classes of weight functions, for example, for classical weights, Jacobi weights, generalized Laguerre and Hermite weights, beta k and alpha k are known in explicit form. There are also some other classes, but not general. In general case, the coefficients alpha k and beta k can be expressed theoretically by Henkel determinants using the moments, but this computation is extremely numerical unstable. It's the, and it needs very big complexity so that it is not be used in construction, only for some school examples for small n. The second way for computing the coefficients in the three-term recurrence relation is to apply Darboux formula with inner products with alpha k and beta k. But there are direct application for large k, again, is very difficult and impossible. In 1982, Walter Gauci starts with an arbitrary weight function and consider the actual numerical construction of orthogonal polynomials as a basic fundamental computational problem. It was in a very famous paper in Science Journal in 82. For a given weight function and given n, generate the first coefficients alpha k and beta k. Then in a series of papers, Walter Gauci developed the constructive theory of orthogonal polynomials on R, which includes effective algorithms for numerical generating orthogonal polynomials with respect to an arbitrary weight function or measure. He considered method of moments and method of modified moments. Then a discretized Stieltjes procedure, when I, after introduce it as a discretized Stieltjes Gauci procedure, adding his name, Lanzer's algorithm. Then Walter derived a strong stability analysis for such algorithms and give necessary software, etc. This theory opened the door for extensive computational work on orthogonal polynomials and their applications in many subjects for arbitrary measures or arbitrary weight functions. I had the luck to collaborate with Walter Gauci just in this time, starting in early 80s of the last century, and we have several more than 15 joint papers. And I work intensively on in this constructive theory of orthogonal polynomials and consider an application that in the theory of S orthogonal and sigma orthogonal polynomials to develop the generalization on Gaussian quadrature formula to quadrature formula with multiple nodes. Then orthogonality on semicircle with non-Hermitian inner product and corresponding quadrature formulas. Also work on orthogonality on radial rays in the complex plane, then integration of fast oscillating function, etc., etc. I will here give a few application of my work in the past. Recent progress in symbolic computation and variable precision arithmetic now makes it possible to generate recurrence coefficients alpha k and beta k directly using original Chebyshev method of moments, but in sufficiently high precision. And such approach enables us to overcome the numerical instability. Respectively, symbolic variable precision software for orthogonal polynomials, as well as for quadrature formulas of Gaussian type, now are available in the Gauci package in MATLAB and our package in Mathematica under title orthogonal polynomials. And these packages can be downloaded from my waves site in Mathematical Institute of the Serbian Academy of Science and Arts. It is a link for that. Here I give some application of quadrature processes. For example, distributions in physics. Bose-Einstein and Fermi-Dirac weights are such weights on zero infinity. Such functions and corresponding quadratures are widely used in solid-state physics. For example, the total energy of thermal vibration of the crystal lattice can be expressed as an integral of this form with Bose-Einstein weight, where F is related to the phonon density of states. Also, integrals with another weight function is appeared in dynamic of electrons in metals. Also, integrals of the previous type can be used for summation of slowly convergent series using the Laplace transform method. Today, moments for the first Bose-Einstein function can be expressed in terms of Riemann zeta function. And also for the second Fermi function, it can be get explicit form for the moments. Using our Mathematica package, orthogonal polynomials, and executing only a few commands, this is for Einstein's weights, we obtained the first 50 recurrence coefficient with the maximal relative error, this 3.3 times 10 to the minus 21. It means that we have all results or coefficients with at least 20 decimal digits exact. For example, Gaussian parameters, nodes and weights for n equal 10 are given by only one command, and the results are given with all exact decimal digits. The second example are hyperbolic weights on zero infinity and summation of slowly convergent series. Here we take two hyperbolic weight function. The moments for the first weight function are given in explicit form. Also for another are given by this, where EK are Euler numbers and the psi of zeta is so-called d gamma function. It means logarithmic derivative of gamma function. How to apply this procedure for summation of slowly convergent series? We take some series with general term defined by small f function, and then transform using some contour integration. Because of that, I called this contour integration method as an integral with some weight function and some function f. Practically, sum from m to infinity can be expressed as this integral, and for alternative series with the function W2 in red here given. Integrand here, phi and psi, are given in terms of the function capital F. It is an integral of small f. Here is real part and imaginary part. Recently, I used another method without construction recurrence coefficients. Namely, if I take such weight function, some square root, something complicated than the previous one, but I can find orthogonal polynomials with respect to this weight on orthogonality on zero infinity, where the coefficients ak and bk are given in explicit form. It is then easy to construct quadrature formula using directly Golub-Welch algorithm. Let D as before, half plane, and f is an integral of f such that the following decay properties hold. Then this series can be expressed as the sum, where pi is real part of f. Now I will say about some application in electromagnetic field problem. Here we consider a numerical method for calculating quasi-singular integrals of the form, this form. F function is a continuous function that defines the distribution of electromagnetic field linear sources. It is distribution of the line charge and current on the axis of the thin linear conductor. And the kernel is usually given by this, R is this distance, and there are some constants here. And we consider a thin vertical linear conductor of radius A and length h, fixed at the origin of the cylindric coordinate system along the z-axis. But problem is when A over h is small, then kernel becomes quasi-singular. And a standard method can be used for calculating such integrals. Here we give some very exact and fast method for this kind of integrals, and it can be successfully extended to other problems of electromagnetic field theory. The method is based on suitable sinus hyperbolic transformation, giving this integral with a new bounds, lower and upper bounds, given by this logarithm. And for n equal 1, singularities in the kernel are completely eliminated by this transformation. So we can use then every method for numerical integration. But if n greater than 1, the integral has pure imaginary poles of order n minus 1. Poles are not on support of the weight, so that they are on the imaginary axis, so that their influence to the convergence of quadrature process can be ignored, because every poles greater than p over 2. But this influence can be significantly reduced using this kind of transformation. In that case, very convenient is quadrature formula, is m-point Gauss-Legendre quadrature formula transformed from 0, 1, given by this formula. And here is interesting that recently Jena et al. In Computational and Mathematical Modeling journal, Springer journal, derived the so-called mixed quadrature formula, MQ. In fact, it is a convex combination of 3 constituent quadrature rules. Such combination of rules can be represented as an 11-point symmetric rule with degree of exactness only 9. Otherwise, the Gaussian formula with the same number of nodes has degree of precision even 21. So that this MQ is not good formula. You can see also it from the next example. We take h equal 1 and a 10 to the minus 3, so that this relation is very small. We have a quasi-singular, strongly quasi-singular integral for this constant, and we use this distribution, the function sinus modulus to the alpha greater than 0. For alpha equal 1, exact values of our integral are given by this, and for alpha equal 2 is this. Alpha equal 2 give the smooth function, because we haven't absolute value in that case. And the results are the same, are the following. MQ formula are very bad. It means number, the error, relative error. It means the number of exact digits in this case is 20. In the case alpha equal 1, it is the function is not differentiable at the points, the 4 points. Therefore, we expect slower convergence of the quadrature process, and we see that for 10, 30, and 120 nodes in log scale, the relative error, but without any additional transformations, is given by this. In this case, if we can improve this using previous mentioned transformation, but improvement is not so big. We get with 120 nodes, it is on the level of, for example, 6 exact digits. Error is 10 to the minus 6. But if we use integration between points of not where the function is not differentiable, then we get the following result. Thank you very much for your attention.